welcome back to the classroom. My name is Mr. Wong. We're going to look at Earth and space. Today's focus will be on the universal gravitational force proposed by Isaac Newton back in the late 1600s, early 1700s. Okay, so as we said, the title of this lesson is Universal Gravitation. Our lesson intention is to identify that objects of mass will exert a gravitational attraction to each other or to another mass nearby, and your success criteria is to look at some factors that play into how strong the gravitational force is and also the acceleration from the gravitational field. So just a quick recap of something we talked about before. Back in the early 1600s, Cardinal Bellamy of the Church and Galileo had a discussion about the model of the universe. And at that period of time, the Church believed the geocentric model was the correct model for how the universe behaved. Galileo, on the other hand, believed in the heliocentric model, so the idea that all planets revolved around the sun. They got into an argument. Galileo could not quite explain the retrograde motion or the epicycles that they were observing, and so history would put it that Galileo got placed under house arrest, but also history would demonstrate that Galileo's idea of a geocentric model was obviously the more correct one as well. We did a comparison on the different types of models and what that would represent. You can see the heliocentric model is a lot more simplistic and it's a lot more clear of how the orbits actually behave. Whereas the geocentric model, you can see it kind of does this multiple spirals and it just keeps going and going, and it's actually quite complicated. It was not a very much viable model of how the universe was structured. Obviously, we now know that both models are not truly correct because there were other galaxies not besides our ones. So at the end, Galileo was more correct, but he didn't have the full picture of the story. Now, the idea of how things orbit around the sun wasn't really explained during Galileo's time. There was no real explanation. And so a guy named Isaac Newton, who just so happened to be born in the same year that Galileo passed away, came up with an explanation of how things orbited around each other. The same idea, or the idea, comes from the apple dropping off a tree. So at that point in time, people already understood how gravity worked. So at the time, people already understood how gravity worked, but how exactly the universe worked to it was a separate issue. See, the thing is, a lot of people interpreted the concept that gravity is about falling, right? Or equals to falling down. Well, they also had a look at, things like other objects in space. Say, for example, we have the sun here, and then we have Earth in this position here. A lot of people believe that all these planets, or even our moon, were stationary in the air. What Newton was able to come up with was the idea that gravity, the way gravity works on Earth, is actually the same in which gravity works in space. We'll talk about that a little bit later on how he actually explains this with a really clever, what we call a thought experiment, but we'll talk about that later on. Okay, so he came up with a mathematical explanation of how things would rotate around each other due to a force known as gravity. This was published in his book called The Principia, and it was our first real explanation of explaining how planets or the moon moves in space. And this is also the same time he invented calculus. So now we know the reason why the moon orbits around the Earth is due to the gravitational force on the Earth pulling the moon in. What what Isaac Newton was able to sort of derive out is that although the moon is being pulled in by the Earth's gravitational field, the moon is also exerting a gravitational force on Earth. Okay, so it comes with this nice little principle. So you might remember what Newton's third law is, that if we have a force being applied to one object, the object will apply an equal opposite force on the other. So have a look at this. You have two mass objects. They both have the same amount of force pulling each other in, but you can see the direction of where the forces is. The blue one is going to the right. Our pink one is going to the left. So equal but opposite reaction force. Sometimes what we actually do is we represent a negative value for the opposite force, in which case it doesn't really matter which one is negative or which one is positive. So to speak, I could say, going in this direction is positive and then going left is the negative direction. Or you could say vice versa. It really doesn't matter. Okay, so let's have a look at this image here. Now, like we said, the reason why the moon is orbiting around Earth is because Earth is exerting a gravitational force on the moon. But if you look carefully at this image here, look at how the moon moves and look at how the tidal waves change around our planet as it moves. So whilst the moon is smaller than the Earth, which means that the consequence of acceleration is slightly different, as in for the moon it orbits around Earth, while as the moon, its gravitational field is actually pulling the water on our planet upwards. So it's pointing towards the moon. So that's the gravitational effect that the moon is causing on Earth. So Newton came up with a nice little formula. It's represented as this one here. So you have two mass objects. Regardless of how large or how small it is, they will both experience the same amount of gravitational force. Okay? As you can see here, we have a larger object here, we have a smaller object here. They both experience the same force, but in the opposite direction. And this is consistent with Newton's third law of motion. You have equal opposite reaction forces. The only thing that will dictate how much force an object experiences is the separation distance from the center of two objects, squared, so r squared, and also the mass of the two objects. Okay? So this is the formula we're looking into. Now some of you might be wondering, what is this value here? What does it stand for? Now big G is what we call the gravitational constant. What we mean by a constant is a number that never changes. Okay. Now, why would we have this here if we already said that the gravitational force that two objects experiences is only dependent on the mass of the two objects and the distance in separation squared? Well, the thing is, G, big G here, actually gives us the units of newtons. So when Isaac Newton came up with this formula, he looked at what he had. So if you have mass, two masses, it's kilograms times kilograms, divided by distance, which is meters, that's the SI units, square. So we get the units of kg square and meters square. But the units for force is newtons, or you could simply write meters per second square times kilograms. You can see the units we have here is not the correct units for force. So Newton actually came up with a additional constant that essentially said, oh, this value can be used to help us find force. And that's where he actually came up with this actual formula for it. So they cancel out with the m squared, kg to the power -2 squared, and you get force. Okay, so that's where that originally came from. So there's that. When he actually came up with the value, when he actually came up with this constant, he didn't actually know what the value was. He just sort of thought that it made sense, so that's how he left it. Okay, let's have a go at some calculation questions using this exact same formula. Okay, so Fred is 75 kilograms, his girlfriend Sue, 60 kilograms, very much attracted to each other, but how much? Find the gravitational attraction between them if they are 0.5 meters apart. Now I know that big G, the constant, is 6.67 times 10 to the minus 11 times the mass of Fred, which is 75, times the mass of Sue, which is 60, divided by 0.5 squared. I'll write the answer here. It gives me a value of roughly 1.2 times 10 to the power of -6 newtons. It's an attraction, so you could say moving towards each other. Or I'll just say attraction. Okay, so that's what the formula is. Now, if you don't know how to get scientific notations on your calculator, when you've done your substitution, press the button that says ENG. Now it'll convert your values into scientific notations if you don't know how to do that. Question 2, it says, what is the gravitational attraction between a small asteroid of that particular mass, and separated by 425 meters? So you do the exact same calculation here. If you know how to do scientific notation on your calculator, this would certainly be very beneficial. So there's that. Over 425 meters square, and that gives you an attractive force of roughly 618 newtons. Again, it's an attraction force, so you can just say attraction. So there's that. What you can actually see is the reason why people aren't colliding with each other due to their gravitational force is because our gravitational force is very small. Gravity as a force is actually one of the weakest forces, or is the weakest force in the world. So that's why you won't really feel a gravitational force until you are next to a larger object. In this case, that would be humans and those who live on Earth. That's why when we jump, we get pulled back down by gravity, right? Because Earth is so much larger than us, it kind of pulls us back in. Usually my favorite way of explaining how a large gravitational field works is when you have two objects collide together, but obviously that's not the case, which is a great thing as well. Okay, so let's go into the significance of the formula where two objects are essentially attracted to each other. Now, this little diagram here is one of Isaac Newton's thought experiments. So a thought experiment is, coming up with an idea in your head of performing a particular experiment that you wouldn't be able to do physically. So look at position E here, or at least our tower here. He came up with the idea that, say you fire a cannonball directly horizontal to, the land, gravity will essentially pull it back to the bottom here. So it kind of drops to the bottom here. He then thought, what if I fire this cannonball horizontally, but faster? And it'll go a little bit further along like so. Now, how do I know that would be the case, or that it would go faster? Early on, when we talked about physics of moving objects, we said velocity is equal to displacement over time. Okay, and this assumption that we're making, we're also assuming there's no air resistance. So let's take that into account. So how far an object will go, let's call it the x because it's horizontal, is solely dependent on how fast it's moving originally times the time it takes to fall down. The time it takes to fall down is due to gravity. So assuming we're launching from the same height and gravity is the same on Earth, then the only thing that can make this object travel further would be by firing it faster. So he says, okay, fire it faster. We get to position C here, but you see the Earth is a sort of circular object. So as it's being fired horizontally, gravity is slowly pulling it. So gravity is kind of pulling it in like that, and so it begins to make sort of this circular motion, but it still falls back onto the Earth. But there comes a point where you're traveling fast enough horizontally that although the Earth's gravitational field will pull the cannonball in, the cannonball is moving so fast that it kind of just floats or kind of travels directly around the Earth's curve. So what we call this is essentially you're falling around the planet. So you're not falling into the planet, but you're falling to the curvature of this planet. That was kind of the genius part of this idea he came up with. Okay, so there's that. Why is this unique? Because that's essentially how satellites work. And he came up with this idea before we actually came up with the concept of sending satellites into space. So the reason why satellites don't usually crash down into Earth is because it's actually traveling at a particular speed, orbiting around Earth. The reason why it doesn't fly away is because it's flying just fast enough that the Earth's gravitational field is pulling it directly in, and it gives us that circular or seemingly circular path. Okay, the same idea happens when an astronaut is in space. They're not floating, they are essentially falling around the planet. And that's actually how satellites work. We don't actually send them up there to float above us, we send them to fall around us. So that's the genius part of Newton's thought experiment. Okay, so the last thing we can look at is predicting the actual gravitational field strength. So we talked about force, but how would we know how strong the gravitational field is around Earth? Well, you can actually see from this diagram we have here, you can sort of think of gravitational fields in terms of how close these imaginary lines are next to each other. The closer these lines are to each other, as you can see around here, the bigger the arrow is, meaning by it's a stronger gravitational field. The further away my arrow is, okay, so as I go further away, you can see the arrow gets smaller. That's our sort of way of depicting it. In essence, we can say that if the arrow lines are really closely packed together, we have a really strong field. If they're really far apart, we have a really weak field. The arrowheads kind of tell us the direction of the gravitational fields. So that's how you can do it as a picture or as a description, but mathematically speaking, we can express it as this formula here. So we can say little g, which is acceleration, is equal to the gravitational force divided by the mass of the object, in which case the force could be your weight force, the mass could be an astronaut. So that's kind of how we can deal with it. Okay. This formula here might look familiar to some of you. It's actually from Newton's second law of motion. So it's F equals to ma. Okay, so that's the formula we have here. So that formula essentially states that if you apply a force on a mass, you will cause an acceleration. Now, acceleration means that there is a change in the speed or direction of the object. So look at this, I have a constant force. Look at my speed, it is continuously increasing. So that's my acceleration here. We can actually get a really fancy little equation when we put these two formulas together, and we get this. So this is acceleration of gravity on a particular planet. Now, why is that different from our original formula, which says this? So what's the difference between the two? Well, this one here is assuming that gravity, or the acceleration because of gravity, never changes. But we actually know there is a slight variation depending on the position of an object on the planet and also in space. So what this actually shows is if we increase our distance away from Earth, we would also decrease the amount of gravitational force Earth puts onto us, and so we have less acceleration. So it kind of looks like this image here. So say we are literally on the surface of Earth, we experience an acceleration of 9.8, as some of you might know. As we go further and further away, you can see how it suddenly decreases by quite a bit here. So if we're at the surface of Earth, we have a gravitational acceleration of 9.8. By the time we reach maybe 36,000 kilometers, the gravitational acceleration on Earth is more like 0.22. So how far we are from the object also will affect the acceleration we experience as well. Also, depending on the value, so we said that on average the Earth's acceleration is about 9.8 meters per second squared in terms of its acceleration. We actually know it does vary from about 9.76 to about 9.83. That's due to the position we are measuring it. So if we're measuring, gravity on top of Mount Everest, that value will be different to if we were measuring acceleration due to gravity on, the bottom of the seabed. So that's kind of what we have there. Okay, so just to finish off, let's do a couple of calculations. So the acceleration due to gravity, let's say on top of Mount Everest, let's look at what that value is. So we're using the formula of gm r squared, but we are also counting the height of Mount Everest. So 6.67 10 to the power of -11 times the mass of Earth. And then we have the radius of Earth plus the height of Mount Everest. That gives us a value approximately 9.76 meters per second squared. And it's going towards Earth. We can write to Earth. And then next one we have is what's the acceleration of gravity on Mars? Well, can do the exact same thing. So using this exact same formula as we have up there, the mass of Mars is 6.42 10 to the power 23, and then we have the distance. Now you can see that we have kilometers here. We need to make this into meters. So 1 kilometer equals 1,000 meters, which essentially means we can time this by 1,000. So it would be 3,390 times 1,000 square. You could, at the same time, write the exact same number and write it in scientific notation like this. It means the same value. So at the end we get a value of 3.73 meters per second square, and that is the acceleration due to gravity on Mars. So you can see how different our gravitational acceleration is on Earth compared to Mars, which is why if you were to jump on Mars, you would take longer to fall back down than if you were to jump on Earth and to do the same thing. So hopefully that gives you a better understanding of how gravity works, and the fact that gravity is caused by two objects attracting towards each other, or multiple objects. If you like this video, or if you found this video useful, please leave a like. I'll see you next time.